Today we are diving into the strategic guide for high rate PCI operation. Our goal is not just to inject coal, it's to master a high performance system that balances efficiency with stability. So our goal is to balance the efficiency and stability, and in order to begin this journey, we must first look at the massive economic and structural incentive that drive our PCA strategy. Now, why do we push for uh, high injection rates? So, what are the reasons? So, primarily, it's about coke replacement. We aim for a ratio of 0.85 to 1.0 kg of coke saved for every kg of coal injected to optimize our raw material cost. Beyond economics, this strategy extends our oven life by shifting the thermal load to the furnace, reducing wear on aging coke batteries. However, achieving these goals depends entirely on the precision of physical injection process. So as you can see, success start at the tuyere in PCI. So we need extreme blast furnace temperatures between these 1000 degrees centigrade to 1200 degrees centigrade, and gas velocity up to 200 meter per second to ensure instant dispersion. The precision lance positioning is the unsung hero here. It prevents uh, ash from depositing on the equipment and ensure combustion happen within millisecond. As you must be knowing that combustion is a very teeny span of time we have to burn in efficient way, and the coal is to be burned in efficient way in raceway. This brings us to the actual chemical transformation the coal undergoes the moment it hits the heat. So immediately coal start burning, just like petrol ignite instantaneously. So in the similar way, this pulverized coal also ignite in the raceway as soon as it pushed through the lance to the raceway. So the transformation is nearly instantaneous. Within just zero point 0.1 second, we see devolatilization, where thermal decomposition releases volatile matter and tar. Immediately after the gas oxidation occur, as this combustible react with blast oxygen to form the initial flame. But the process doesn't end with the gas. We still have to manage the solid residue, and this is one of the most important part, uh, um, especially the car reaction in the raceway. So once the gases are gone, we are left with solid residue or car. This stays. The car reaction is a heterogeneous process where the car reacts with CO2 and S2O in the post flame zone. Understanding this sequence is vital because this reaction defines the environment of the raceway, which is the heart of our furnace. Now, coming to the dynamics of the raceway as it is shown in the slide. The raceway is where the magic happens, and here oxygen is rapidly consumed near the tuyere nose. As we push higher injection rate, we actually shift the combustion focus closer to that nose, while this is where we achieve our coke replacement. It also brings us face to face uh, mm, with the operational barriers that can limit our progress. So, what are those operational barriers which are limiting operational barriers which are limiting our injection potential? So, uh, managing operational barriers is now becomes a challenge. So, as you can see, um, mm, pushing the limits means eventually hitting what we call the three major process walls, and these represent the physical and chemical limit of our furnace. So to overcome them, we must understand exactly what each wall consists of and how they threaten, how they challenge our stability. So understanding fully about these will be fruitful in achieving the desired result. So coming to the this slide, first is the thermal wall, where endothermic coal reaction can cool the flame too much. That means flame temperature drop. Second is the permeability wall, where unburned car accumulate and block gas flow. And the third or the final, we can say, the chemical wall involves the increased sulfur part, uh, increased sulfur part and ash load, which is entering to our slag. So navigating these walls require us to keep a constant eye on our critical performance indices. So we manage what we measure. To stay safe, we maintain theoretical flame temperature TFT between 2000 and 2250. We also track our stoichiometric oxygen ratio, keeping it above 0.70 to control unburned car. If our total delta P, that is delta P is bottom and top subtraction. If this rises more than 3%, then it's a sign of fine accumulation. So this becomes a one of the good yardstick to diagnose. If such thing happens, then operator can try to cross check this also as a reason of rise in delta P. Now these metric guide our daily shift rules. Now coming to the our next slide, our operators use specific thumb rules, and which is important thumb rule to so our operators use specific thumb rules to stay in the green zone. So for every 10 kg increase in PCI, we must raise the blast temperature